In this video, we're going to write ionic compounds with our friends, the polyatomic ions. Now, this chart with polyatomic ions is in your book. It is on page 98. Page 98. And so we said earlier to bookmark this. Fold over the corner, put a little sticky note in here. You don't have to memorize the polyatomics, but you do need to know when to use them. And so whenever you're looking at a name of a compound that ends in ATE or ITE, the eights and ites, those are the polyatomic groups. And that's when I need to know, look them up. Look them up on this chart in my book. And so you can use this chart on any test or quiz where you would need polyatomic ions. We just have to know when to use them and how to use them. So in this example, we're going to write the formula of calcium carbonate. Calcium carbonate in seashells and chalk. Okay, so again, there's no way around writing formulas without getting the charges. So I see calcium, and obviously like this is what I would be given, just the name. Write the formula for calcium carbonate. I see calcium, so I look it up on my periodic table. It's in group 2. And I wrote in that the charge is always +2 or 2+, just like they have here, calcium. You can write 2+ or +2. When I notice then that the second part of the name ends in ATE or ITE, the eights and ites, I'm looking it up on my polyatomic chart. Carbonate, carbonate, carbonate. Here it is. So you don't have to memorize this. Carbonate is CO3 and the charge is -2 or 2-. Fantastic. And so all these ionic compounds, even though with polyatomics they get a little more complex because they end up with more than 2 types of atoms, more than 2 elements, ionic compounds always still just have 2 charges. There's the positive charge and the negative charge. That's all you have to balance, a positive and a negative. So if you are a charge balancer, you're going to look at that right away and say, done, right? You're going to say, I'm done. There's 1 calcium and 1 carbonate. +2 -2, it adds up to 0. It's neutral. Game over. It means that the calcium is going to donate 2 electrons, and in order to bond carbon and 3 oxygen and give everybody an octet, I'm going to be 2 electrons short. So that CO3 group needs to gain 2 electrons. Perfect. Calcium's got 2 to donate. 1-to-1 ratio. The charges are neutral right away. Now you can do the crisscross thing too with polyatomic ions. That's fine. You just take this 2 and this 2 and you crisscross them. Now when you need more than one of a polyatomic group, you'll see it written in parentheses. I mean, if all I did was like crisscross the 2, I mean if I wrote Ca2 CO3 2, then it looks like there's 32 oxygen. And that's a little bit crazy. That'd be a lot of oxygen, right? Well, that's not what I'm looking for. If I'm crisscrossing the charges, I mean like I want 2 groups of carbonate. That's like a group deal. And so that's where in here they're showing the CO3 group in parentheses with the 2 on the outside. Now that shows that I have 2 groups of CO3. Oh. But now do you see what happened? I crisscrossed a 2 and a 2, which in the end, I need to report my formula as the simplest repeating pattern of the crystal. Well, 2 to 2 would then always simplify down to a 1-to-1 ratio anyways. So your final formula doesn't need the parentheses. If you put them in there, I would never mark it wrong. So if somebody did still keep them in, it's not wrong as long as you have the formula written as CaCO3. You have to have them if you want more than one of a polyatomic group. Oh, interesting. And in the end then, yeah, it should add up to 0. There's one calcium and one group of carbonate, +2, -2. Neutral, right? Okay, so kind of similar would be something like this guy, baking soda. So with baking soda, I've got my positive ion and my negative ion. They would give me this. I would be told, whoa, didn't mean to write all over it. I touched it with my sleeve. I would be given that, like the name, sodium hydrogen carbonate. And then I'd be asked to write the formula. Okay, well, I see sodium, and so I know sodium is Na, and I have to find the charge, and so I look at on my periodic table, sodium's in group 1, everything in group 1 is +1, or 1+. Then if you see that the final ion, the negative ion that's in the back, if you see that it ends with ATE, that's the red flag to go to the chart. Go to the chart. I bet it's on the chart. Hydrogen carbonate, hydrogen carbonate. It is on the chart. Here it is. And I knew to go to the chart because it ended in ATE. Eights and ites. You got to look them up unless you want to memorize them. And then I have the formula and the charge. So then I can say, oh yeah, the formula is HCO3 and the charge is -1. Oh, well, +1, -1, that's neutral right away, right? So I could just be done with it. The sodium will donate 1 electron. If you want to bond a hydrogen, a carbon, and 3 oxygens, you can. But in order to give everybody an octet, you'll be 1 electron short. And so the sodium will give that 1 electron to the HCO3 group. In the process, they must bond together. They're bonded together for life. And so if you want to crisscross, I guess you can. But if you're just crisscrossing ones, you're not going to write them in the formula anyways. Okay, so here might be just a couple other examples. Let's write a couple examples of things that might come up. So what if I were given something like potassium sulfate? I want to write the formula of potassium sulfate. Okay, well, I need the charges, right? I need the ion charges. Potassium is K. It's in the first group. And everybody in the first group is +1, or 1+. I notice that my second ion ends in ATE, so I gotta look it up. Sulfate, sulfate, sulfate. Here it is. And so I've got the symbols, SO4, and I've got the charge, -2 or 2-. I don't know, just since I was a baby, I've been writing -2. But 2- is fine. Okay, so if I'm a charge balancer, I've got my charges, and I'm going to say I need to make these add up to 0. So potassium would like to donate 1 electron, but sulfate needs 2. Well, +1 -2, why don't we just take 2 potassium? If I have 2 potassium, that'll give me a total charge of +2 on the front, and that'll balance with my -2 on the back. Then any multipliers turn into subscripts. If I needed to multiply the charge of potassium by 2, then I need 2 potassium ions in my formula, K2SO4. Done! Now you would again get the same thing if you were a crisscrosser. If you were a crisscrosser, you would be crisscrossing the 2 and the 1. And I don't have to bring down the 1. So I need 2 potassium and 1 sulfate. Cool, right? Like these polyatomics look kind of wild and crazy, but it's a lot of the same rules that apply. Let's do one more. What if I gave you something like this? How about copper? Should we make this a tricky one? 2 phosphate. What if I go copper 2 phosphate? Okay, so I got to find my charges. Copper is a transition metal, but the 2 is telling me the charge, so I don't have to look it up. That Roman numeral 2 means that copper's charge is +2. Phosphate ends in A-T-E, and so I look it up. Phosphate. Ooh, it's right by my copper. Here it is. PO4, and the charge is 3 minus or minus 3. Either's fine. Okay, so I find the charge. I have to find the charge. Then, if I'm a balancer, I'm going to say, I got to make this add up to 0. And there's really nothing I can do to just one ion to get them to add to 0. So common multiple is probably 6 again, which is kind of a common combination to have like a 2 and a 3. So if I multiply the copper times 3 and the phosphate times 2, I would get a +6 minus 6. And what that means is that the copper will donate a total of 6 electrons. Each copper has 2 to give, so if I have 3 copper, I'll give a total of 6. Well, the phosphate group wants to take 3. So if I have 2 groups of phosphate, I get the -6, meaning that all 6 electrons are gained. All 6 are transferred. Then those multipliers become my subscripts. So I need 3 copper and 2 phosphate. But if I just put a 2 down here, it looks like PO42. And I don't mean for there to be 42 oxygen. I mean that there's 2 groups of phosphate. So I must put phosphate in parentheses. And so my final formula should kind of look like Cu3PO4 with a 2 on the outside. That means 2 groups of phosphate. Oh. So you have to use the parentheses when there's going to be more than one of that polyatomic group. In the case of potassium sulfate, I only needed 1 sulfate, so parentheses technically would be optional. If you put them in, it's fine, but you don't need them. And now with the copper 2 phosphate, if you are a crisscrosser, you're going to get the same thing. You would crisscross the 3 and the 2, but you wouldn't bring down the plus or minus. And either way, it's going to look like there's 2 groups of phosphate, and so you would have to put the phosphate in parentheses.